Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. We are going to continue discussing about the application of radioactive isotopes. Especially in this class we will talk about how we apply particular isotope systems in aquatic geochemistry. Okay. So, yesterday we were discussing about dating. I think we ended with dating, and we discussed about the dating equation and how we are going to select particular isotope systems based on the objects that we are trying to date, whether it is object which is a very old rock, then you have to use isotopes that have very long half life, or you are going to use a water. For instance, if you are trying to trace groundwater recharge, then you are going to use isotopes that have very shorter half life. Say for example, 3 hydrogen, that is tritium, and then you will have an isotope which will show you a lot of variations and you can exactly date that. So, the ranges of the dates that is expected, and therefore, you select a particular isotope system. Okay. Now, for all geochemical applications also, if we are going to date very old rock. So, yesterday I showed you a table where you had many nuclides which were cosmological nuclides. What do you mean by cosmological nuclides? That means they are produced due to some cosmic spallation processes. Okay. That means they are there in the due to natural processes, cosmic processes, due to cosmic rays, they are getting produced. Okay. But here in if we are, and most of those elements you would have noticed were the lighter isotopes. Okay. They would be of the lighter mass number. Okay. So, you would see there were mostly hydrogen, then there was some aluminum, beryllium, sulfur, chlorine, sodium. Their mass numbers were below iron. Okay. Now, only heavy atoms such as you see uranium, or you see strontium, rubidium, okay, samarium, neodymium, these they are of very high masses. Okay. Their masses, for instance, you see uranium has a mass that can vary from 234 to 238. Okay. So, they have quite heavy masses as compared to hydrogen, or aluminum, or beryllium, or sodium. Okay. So, they are the very different kind, their isotope systems are behave little differently. Okay. And they have very long half lives, extremely long half lives, and therefore, they are what do I say, how do you select them. Okay, depends on the item that you are going to expected dating range. For instance, if you are trying to date earth, okay, we want to date earth. So, we are going to look for something which is in the billion of years range. Okay. We are going to need a particular system, an isotope tool that can help me get to a date which is in the range of few billion years. Okay. Same thing for the universe also, it will be in few billion years. Okay. So, for that I need a system whose half life is in that range. Why does half life matter? In the previous lecture we showed a plot where we were plotting concentration, and we were having number of half lives. So, 1 half life, 2 half life, 3 half life, 4, 5, like 6, 7, like that. And you could see that after beyond 5 half lives, the value did not change much, right. Beyond 5 half lives, the value did not change much. So, we want to be in the safe zone. Okay. We want to be in this 5 half life period. Okay. So, for that half life is very important, knowing half life, accurately knowing half life is very important. Okay. So, when you are going to date rocks, when you are going to date minerals, and we are going to date something which is very old, then we are going to use the more heavier isotopes. So, it can be starting, you see it can go from 40 potassium. Okay. 40 potassium has a half life, very long half life, actually 1.28 into 10 to the power 9 year. Okay. So, that it breaks down into 40 argon and 40 calcium, and we are going to measure this ratio. This is the daughter ratio. If I am going to measure 87 rubidium which breaks down to 87 strontium, okay, we are measuring 87 strontium by 86 strontium ratio, okay, and it has a half life of 48.8 million years. Okay. So, you just see now it is just the how variable it is. So, lanthanum, okay, lanthanum it breaks down into cerium and barium, very high, 2.59 into 10 to the power 11 years. Okay. Samarium, neodymium, alpha decay, okay, 106 billion years. Okay. So, if we have depending on what we are going to use, okay, depending on what we are going to use the dating, like what is expected range of dating it will be, we are going to select our isotope systems. Now, let us look some we are going to use this parent isotopes, right. But in our earth that this is a group of elements which falls under the lanthanum actinum series, and they are not very high concentration. Okay. So, except for potassium and rubidium here, okay, these are mostly trace elements. Okay. So, except this one is a major element, okay, this is a major element, rest this one is a trace one, okay, and these are all extremely rare. Okay, they are extremely rare in their concentration. But how does their concentration, why I am talking about suddenly about concentration? Because if just imagine how their distribution is, okay, on the earth's, how they are differentiated in the earth's internal structure would control how much they are in the individual, how much we are going to get these daughters in those reservoirs. So, for that we are going to look into something called the compatible and incompatible elements. Okay. For that we are going to look into this differentiation first, that is how do we differentiate into compatible elements and how do we differentiate into incompatible elements. I am just going to come to this. Okay. Now, I know many of you are not direct from earth science background, but I hope you know the structure of the earth. Okay. This picture in our left top corner, this shows the earth's structure. Okay. So, the earth has the crust and then it has a mantle, okay, and in between that there is a asthenosphere, okay, which is a soft mantle, okay, that is the topmost mantle which is the asthenosphere, and then we have our lower mantle which is below the asthenosphere, then we have the outer core which is liquid, and then we have the inner core which is absolutely solid. Okay. So, we have the inner core, we have the outer core, we have the lower mantle, we have the upper mantle, and we have the crust. Okay. And all the elements, okay, they are differentiated based on their affinities. So, in one lecture we talked about different elements which has different affinities, right. We talked about some elements which are more lithophile, okay, which are more lithophile. some elements which are more chalcophile, okay. Some elements which are more siderophile. Okay. So, different elements will fall in this category, right, different elements will fall in these categories. So, lithophile, which are those? They are the silicate loving, they will love to be on the earth's crust, the outermost crust, because that is where silicate mineral phases are mostly found. Okay. So, they will love to be in the silicate rock phase. Okay. So, they will love to be with the silicate rocks. Now, how are silicate rocks produced? Okay. So, for that we need to understand two things. Okay. First, a little bit of how magmatic activities occur, that is the production of igneous rocks. I am just going to give you very brief understanding. Okay. What happens is, suppose you know that this mantle, okay, this mantle is melting. Okay. This mantle melts. Why a mantle melts? There are various reasons. If you are curious, you can go and look for all the reasons. Different reasons cause mantle melting. Plate tectonics is a very one of the most dominant reason why mantle under different tectonic activities will undergo melting. Now, what happens when the mantle melts? Okay, some pockets of that magma moves into the earth's crust. Okay, it moves into the earth's lower crust, and then it looks for weak joints, weak spots through which it can erupt and release the pressure, because it is under a lot of pressure. Imagine it is like a hot, very hot gases, very hot liquid, and all that is placed, okay, and it is huge pressure. Just imagine it is inside the earth. Okay. So, it is deep down inside the earth, it is being pressurized from all sides, it is also burning, that means a lot of gases is also getting produced. So, it is enclosed now, it wants to erupt. Okay. So, I think many of you must have seen how a volcano erupts. Okay. So, just imagine that much amount of pressure is kept inside a chamber. Now, when the magma is there in the chamber, okay, as it is erupting through so this is the first magma body, it gets placed in the earth's crust where there you have a host rock, okay, and it finds all kinds of fissures, okay, all kinds of fissures and weak joints and all that, through which it can it can rise and it can lead to an eruption. So, as it is erupting, okay, as it is erupting, it starts to lose the pressure. Slowly the temperature also slides, drops, slight drop of temperature happens. Okay. As soon as there is change in temperature and pressure, what will happen? Whatever is there in the magma, okay, so whatever is there in this magma, it will start to cool down. Okay, this magma itself starts to cool down. When it starts to cool down, it will start forming crystals, okay, crystals of different minerals, okay, and that also has a a series of which crystals will form first, and there is an entire series of how crystals get formed from different types of magma sources. Okay. Now, as this crystals is getting settled, okay, certain elements will have the tendency to go to certain minerals and be less available in the liquid. Again, so certain elements, say for instance, let us take this element called rubidium. Okay. Let us take this mineral called rubidium. Okay. rubidium is an incompatible element. Okay. It is said to be an incompatible element. Why is it called an incompatible element? That is because when the magma is there, okay, when mantle is getting melted and this magma is getting formed. Okay. So, from mantle I am going to form my magma. This rubidium will prefer to be in that magma and get inside the magma chamber. Okay. My rubidium is an incompatible element. Okay. This rubidium will prefer to be in the magma and it will get in the magma chamber, and as the crystals are forming they will be having higher rubidium. Okay. So, my rubidium is incompatible in the mantle, it does not like to be in the mantle. Okay. It will like to be with the magma, okay. It likes to go out with the magma, and then from the magma it will form all the different types of minerals that is getting formed here, the crystals that is getting formed here, okay. They will have higher rubidium. So, mantle will start losing all the rubidium, okay, to the magma with more and more magmatism. Okay. As the magma is getting formed, all the rubidium will become shift to the magma, they will leave the mantle, they will go to the melt phase. Okay. And as it is this magma which is now getting separated, now it is separated from the mantle and now it has been emplaced in the earth's lower crust from where it is erupting. Okay. And as it is erupting, it has also started to crystallize. Now, these silicate minerals which is now getting crystallized, they will now have a high rubidium concentration. So, therefore, this igneous rocks, these upper crustal rocks, okay, have high rubidium. These upper crustal rocks will have higher rubidium. Okay. Again, so my rubidium is a incompatible element. So, when my mantle is melting to form magma, my rubidium will prefer magma over the mantle phase. It will prefer to be in that liquid phase, that is the magma phase, and this magma gets emplaced into the earth's crust, okay, the lower earth's crust, and then as the magma is getting cooled, okay, as new crystals are getting formed, this rubidium which is now in high concentration in this magma, this starts to form crystals. So, all my upper crustal rocks will have higher rubidium, okay. They will have a higher rubidium. Now, we also know that rubidium will decay and produce strontium, right. Rubidium will decay and it will produce strontium. So, wherever my rubidium concentration is high, my radiogenic strontium concentration will also be high. So, my crust, okay, that has more rubidium, okay, that has more rubidium than the mantle, okay, as compared to mantle, then the crust will have more radiogenic strontium as compared to the mantle. So, my crust has more radiogenic strontium as the mantle, okay, will have more radiogenic strontium as compared to the mantle. Okay. This is how we talk about compatible elements and incompatible elements. We also saw another system, for example, samarium that produces neodymium after and alpha decay. Samarium is a compatible element, just the opposite. So, samarium is a compatible element. Okay. It is a compatible element. That means, it would like to stay in the mantle. It likes the mantle, it will stay within the mantle. It will not prefer the magma phase. Okay. It does not like to be in the liquid phase. So, what will happen? This magma, when it starts to form all the igneous rocks, when it starts to form the crystals and all that, these rocks, okay, these upper crustal rocks, they will have a lower samarium. Okay. They will have the lower samarium. Okay. And you see, samarium is going to produce neodymium. Okay. Samarium is going to produce neodymium. So, wherever my samarium is going to be high, my radioactive neodymium will also be high. Now, since samarium is going to be high in the mantle, okay, this samarium is going to be high in the mantle, my radioactive neodymium will also be high in the mantle as compared to the crust. So, this is how we understand, this is what is the importance of compatible elements and incompatible elements. Okay. We need to understand how particular elements, they are going to be in the different kinds of reservoirs, such as the upper crust, such as the lower crust in the mantle, okay, where they are expected to be more, and therefore, where do I find the radiogenic daughters. Okay. So, that we need to understand which are compatible elements, which are incompatible elements. So, first let us see a few other types. So, there is one group which is called the mantle rock forming elements. Okay. These elements, okay, they will be mostly be in the minerals that is commonly found in the mantle. Okay. For example, in the earth's mantle, we have, what do we have? We have olivine, okay, we have pyroxene, we have anorthite, we have spinel, we have garnet, and all these are mostly made up of these elements. Okay. And there are other trace elements. So, these are the major elements, and they will, all the other will be in the tracer component. Okay. That means, they will not be in their own, but they will be in the all the dislocated sides, they will be as impurities. Because of similar radius and all that, they might get exchanged in some other elements place. For example, in often you will see we find that strontium sometimes can replace calcium. Where calcium was supposed to be, in that place we are going to find strontium sitting. So, that is just because of how similar they are geochemically. Okay. If the atomic position allows that kind of substitution, so often we see similar elements will substitute. Okay. So, that is why they will be present as impurities, and they will be in trace amounts. They will not form the minerals absolutely of their own, because they are so less in quantity, they will just be present as impurities. Okay. So, these are the compatible elements, they are the mantle rock forming elements. Okay. Otherwise, there is another group which is called the incompatible elements, and this group again is divided into two groups. We have already discussed, one is the lithophile group, that is the silicate phase loving elements, okay, and the other is the HFSE group, high field strength elements. Okay. So, what are the lithophile elements? You can see here we have potassium, we have rubidium, we have cesium, we have europium, we have strontium, we have lead, we have barium. Okay. These are all the lithophile loving elements, and that is they are incompatible, they are incompatible in the mantle, and therefore, they will be enriched in the earth's crust, because the earth's crust is formed from the melt that was generated in the mantle. Okay. This mantle melting continuously over earth's lifetime has created the earth's crust. Okay. So, they will be more enriched in the earth's crust, and these elements, they are also very fluid mobile, and hydrothermal alterations can easily change their values. Okay. Their concentration, they will be easily mobile, they are very soluble, they are very mobile, they are very prone to alterations. Okay. So, they will get altered if there any hot liquid is there, if they will they are more reactive in nature as compared to another group of elements which is called the HFSE elements. Okay. These elements, although they are also enriched in the earth's crust, they have, as you can see, their ionic radius is quite small, and what is more important is they are of higher cationic charges. Okay. So, 3, 4 plus 6, they will be higher cationic charges. So, what will happen is that their Z by R ratio is going to be high. Okay. That means higher cationic charge and lower ionic radius, which will result that they will have very strong bonds with the anions. Okay. They are going to be having very strong bonds with the anions, and they will start having a very high electrical field strength. So, they will have a lot of their bond will be very strong, they will have a high electrical field strength, and they are almost usually immobile, they are mostly immobile in nature, and very resistant even to metamorphism and hydrothermal alterations. Okay. So, they will form what we call the heavy minerals. Okay. They will be mostly in the form of refractory minerals. Okay. They will be the heavy minerals, refractory minerals, minerals that do not erode, they do not get altered. So, I hope this is clear how we differ between compatible and incompatible elements. Now, let us take up this particular system called rubidium strontium system. Okay. And we are going to look into details how this system is applied in aquatic chemistry. So, I have already explained two things. First thing is rubidium is a very incompatible element. Okay. In fact, it is more incompatible than strontium. That means, given rubidium and strontium, rubidium will prefer the melt phase, that is the magma phase, more than the strontium. Okay. So, rubidium will be more enriched in the earth's crust as compared to strontium. Okay. So, therefore, their occurrence in the earth's continental crust will be very high. And 87 rubidium is radiogenic, it will produce 87 strontium. That means, earth's crust will have more radiogenic strontium, it will have more radiogenic daughters, because the parent atom, that is 87 rubidium, is higher in the crust. So, we are going to use this particular differentiation value. So, let us look into this picture where we have in the x axis we have time, and in the y axis we have 87 strontium by 86 strontium. Okay. So, we have the 87 strontium by 86 strontium, which we are generally measuring using a multi-collector ICP-MS. And you see a few curves, you will see a few values here. Okay. So, first thing that we are going to note down is the initial value of the solar system. So, when Earth got formed, that value. So, consider that value is here, that value is here. Okay. And if it is getting as time is progressing, my radiogenic strontium is going to get produced because of the decay of 87 rubidium. So, this is how the bulk earth is going to change. This red line shows the evolution, okay, shows the evolution of bulk earth. Okay. That means there is no differentiation, it is total earth, there is no differentiation into crust, mantle, no. Okay. So, there is no such differentiation has happened. But what do we know? We know that actually differentiation has happened. So, this is basically a theoretical line. Okay. This is basically a theoretical line. What do we know? That after the formation of the earth, there was a differentiation. The mantle, the core, the crust, they all got differentiated. Okay. When it got differentiated, what happened? Rubidium preferred the crust, okay. That is, with the melt phase, it moved out and it got enriched in the crust. The mantle now is depleted, okay. We say depleted, has low concentration. So, this is my low rubidium by strontium mantle. This is this dotted line, okay. This dotted line is my low rubidium by strontium mantle, okay. But what we also know, and why do we see that the radiogenic value is very low? Because obviously the rubidium all got into the melt phase and it is there in the crust, okay. So, our mantle has a lower radiogenic value as compared to the theoretical bulk earth value, okay. Now, let us see what happened to the crust, okay. This is the progression of the earth's crust, that is, high rubidium by strontium crust gets created, this line, and now it is moving on a higher side, it will just move like this. Why? Because as we are as the age is moving higher, it is going to produce more and more radiogenic values. The radiogenic values in the crust will increase with time. Right. So, it will increase with time, and just the opposite will also happen, okay. Just the opposite will happen for the mantle, okay. You see the mantle, the curve gets like this, okay. The curve starts to get lower. Why is it getting lowered? Because with every melting event that is going in the mantle, okay, every melting phase that is happening in the mantle, the rubidium is getting out, the rubidium is going out with the melt phase, the rubidium is coming inside the earth's crust, okay. So, my mantle is getting depleted in my rubidium concentration. With time also, my mantle is getting depleted in rubidium concentration. So, even though my time is going to increase the radiogenic daughter, my parent atom is disappearing. So, due to this low rubidium strontium, which is gradually basically decreasing with more and more melt mantle melting events that is happening. Therefore, my mantle is going to have this kind of signature, lower signature. So, it is a continuously depleting mantle. So, it is going to get depleted, it is going to go more and more lower values. Okay. So, therefore, it is written continuously depleting mantle. So, here we start with a bulk value. Okay. We start with a bulk value. So, this is when the earth getting formed, and if nothing would have differentiated, we have this red line, that is the bulk earth value, and now that is only increasing from this value to this value because of the radiogenic decay. So, 87 strontium is going to get produced from the decay of 87 rubidium, and therefore, from the bulk value we are moving to the bulk earth value in 4 billion years time. But what happened was, there was a differentiation event and my crust and mantle got separated, and when that differentiation happened, my crust started having high rubidium by strontium ratio, and because now my crust has high rubidium by strontium ratio, my 87 strontium by 86 strontium of my crust was also high, and it is going to increase. Why? Because as the crust is changing, evolving, and more melted mantle melt is getting incorporated in the crust, more and more rubidium is coming into the earth's crust. Okay. So, we are having more accumulation of the radioactive parent on the earth's crust as compared to the mantle. So, therefore, the evolution of the earth's crust will be like this, and just the opposite thing will happen to the mantle. So, this was the original mantle, but we are going to see a continuous depletion. Okay. The mantle is also melting, it is losing all the rubidium to the crust, and therefore, it is slowly going to get more and more lower values. Okay. So, this kind of differentiation helps us understand okay, what is of crustal signature, what is of mantle like signature. Okay. Clear differentiation between my crustal signature and my mantle signature. So, this 0.716 is more crustal signature, 0.700 is more of my mantle like signature. Okay. And this is how we are going to use these two values. Okay. Even if they are changing in the second decimal place and the third decimal place, we are going to use this difference in understanding very important processes. Okay. We are going to look into more details in the next lecture.